Okay, so let us get started with what we were doing last time. So, we are discussing the basic issues, few basic issues in real time operating systems. We had halfway discussed about the clock interrupt processing. It said that whenever a clock interrupt occurs, and these occur very frequently, the kernel carries out three main tasks. It checks whether any timer has expired and then queues the corresponding action as a task. Sorry. Okay. So, yeah, these are the three things. It processes the timer events for each timer. It checks whether it has expired and then queues the corresponding action. It updates the execution budget of the currently executing task and then updates the ready queue. In the processing timer event, we had said that the timers are arranged in a queue and each timer is associated with a handler routine, and after the timer expires, the handler routine is queued. And then we had said that after each clock interrupt, the scheduler decrements the remaining time slice for the task, and then once the time slice becomes 0, the task is preempted. Some events might have occurred since the last clock interrupt, and based on that, actions are taken. Maybe the currently executing task might have to be preempted if a higher priority task becomes ready. Now, we are discussing about the clock resolution being supported by the operating system. We had said that the current hardware clock that is available is a gigahertz clock. Should be possible to have nanosecond clock, but the granularity that we will discuss in our subsequent lectures is microseconds, several microseconds or even milliseconds, and we are trying to examine the reason behind this. The reason is that the clock that we are referring to is a software clock which is maintained based on the hardware interrupts, and then we were trying to answer the question that even the software clock, why can't it be a nanosecond software clock? The answer is that whenever we try to get the clock time, we need to invoke a function. Do not directly read the clock time, because it is an operating system function, for example, clock get time. So, let me just discuss about that. So, the response to a function invocation is not deterministic. It is not that every time it will complete. If it takes few clock cycles to execute, it is not that it will always execute in that much time, because it depends on what task currently running, whether there are other interrupts and so on. So, this variation in the completion of the get time function is much larger than several hundreds of nanoseconds. A software clock of any finer resolution would not be meaningful, because the time that you read, there is a variation in the times. If you read it as some 100 nanosecond, it may be 110, it may be 105, it may be 100. So, there is a jitter there, right. So, if you make the clock any finer than the jitter that is there in the get time function, the clock is meaningless, right. You are maintaining a clock, but the time that you read is not exactly that time. So, that is one reason. The other reason is, of course, as some of you are saying, the overhead involved in maintaining the software clock. The more frequent need to increment the software clock, the greater is the amount processor time servicing it. But sometime you need to read the nanosecond clocks. There are some events which would require you to compare with the time that has elapsed up to a nanosecond accuracy, and we will see that many of these operating systems, they do not really use the software clock to provide a nanosecond clock that can be read by the task, but what they use is a hardware timestamp counter. While discussing the operating system, we will just point that out. Even while discussing the POSIX standard, we will discuss about this. The nanosecond clock time can be read through a memory mapped address space of the real time tasks.
Even for the other events, why
yes.
do we use separate software timer? Why can't we directly read the timer from the hardware clock? Why a separate software clock? It should read from the hardware clock itself.
Okay, so let us look at the answer to that question, that why not always use this hardware timestamp. See, the answer is that we do not really see that might give you a value of a 32-bit something, right. You do not need that, you need the current time, the time it has, or you want to set a timer. You can't directly use the hardware time for most of the applications. And the other problem with the hardware timestamp is that it has portability problem, because you are directly using the hardware, it is a memory mapped. If there is any change in the configuration, use a different processor, all your applications need to change, right. So, this has a problem. So, unless the application requires it, do not use the hardware timestamp, and this is also not supported by many of the operating system.
And how are these issues handled in such as services where hardware is?
See, if you need a nanosecond granularity for some time application, the application will have portability problem. It will use the hardware clock and it is a difficult application. Okay, let us proceed from there. Now, let us look at the kind of timer services that will be provided by these operating systems we are going to discuss. The timer is a vital service for any real time operating system. Actually, we had said that this is one of the characteristic that differentiates the traditional operating systems with the real time operating systems. Actually, all these real time operating systems that we will discuss, they will have two types of timers. All these real time operating systems, each task can set several periodic timers and also several one-shot or aperiodic timers. So, if you look across the tasks, then there will be many periodic timers and one-shot timers that can be set. A periodic timer is typically used for sampling events at regular intervals, like you want to do something every 10 millisecond or 100 millisecond. You set the clock, the periodic timer, and then each 100 or 10 millisecond it will keep on giving an interrupt, right. Based on that, you would have the handler routine to handle the reading some sensor value and so on. So, that is one main use of a periodic timer. Now, let us look at the aperiodic timer also, we will see what is its main use. And the timer is set once, the periodic timer is set once, and once it is set, periodically it will keep on giving timer interrupts, and each time the periodic timer expires, the handler routine will be invoked, and again it will be reinserted in the timer queue. So, the timer has expired, again in the timer queue we were discussing, the timer will be again reinserted with its expiration time updated. So, this has expired, and then the handler routine will be invoked, queued actually, not invoked, it will be queued, and then again this same timer will be inserted back in the queue with updated expiration time. A one set timer, once it is set, will expire only once, as the name itself says, and these are popularly known as watchdog timers. Very popular name for all real time programmers is a watchdog timer. Now, the watchdog timer is used very frequently in any real time programming. The main use is in determining whether a task is missing its deadline, and if the task misses its deadline, then the handler routine with this timer will initiate some exception handling routine. So, this is the typical structure of a real time task. So, you first set the watchdog timer, this is the system call, set the watchdog timer. Let us say we say that watchdog timer start for 10 millisecond. So, the watchdog timer will expire only once after 10 millisecond, and if the process does not complete by 10 millisecond, then the handler routine here will be invoked. You have to attach a handler routine with a one set timer that I have not shown here, just saying that watchdog start watchdog timer, and if the process completes before the watchdog timer expires, that means it has completed within its deadline, then we do not need the handler routine to be invoked, just say WD tickle. So, this is the system call that is invoked to reset the watchdog timer. So, this is typically the structure of every task to check whether the task is completing within its required time, otherwise an handler routine will be invoked.
Here the timer is reset for some other process.
No, this is the one, this is the WD start is the watchdog timer which is set. Now, if the task completes, we do not need the handler routine to be invoked, the exception handling did not occur. So, it has completed, let us say 10 millisecond it is set, and by 7 millisecond we find that the processing is over. So, then this system call will be given WD tickle, which will take out the watchdog timer from the queue. It has completed within time, no exception handling is required, the watchdog timer will be disarmed. But if the processing takes more than 10 seconds, the watchdog timer will fire in the timer queue and the handler routine will be invoked. Now, before we start discussing about the real time operating systems, we need to understand some basic issues on Unix, and these are slightly different from what you had done in your first level operating system course, something other than that we will be discussing, because we will see that many of these real time operating systems, they are actually based on Unix variants basically. So, if we look at the history of Unix, developed at AT&T Bell Labs 1969, written in assembly language, and it was rewritten by Rajib in C language in 1973. But Bell Labs is a telecom company. They did not foresee that how they will use Unix commercially, and since it was a very good operating system and they did not have much use for it at that time, they make it a freeware 1975. There were many recipients, or many could get the source code of Unix, and then based on that many variants of Unix kept on appearing. The first one was possibly the BSD, the Berkeley software distribution. So, here the Unix source code, the University of California at Berkeley, they got a large project where they incorporated TCP/IP into Unix, and they came up with a socket. The BSD was the first to support socket in Unix. That was of course a major improvement to Unix, networking support on Unix. And then 1985 the X Windows was incorporated. So, all Unix distributions that you get now have X Windows in it. It is for the graphical interface. And then the web support, and then the Linux appeared 1996. But there were several other variations of Unix based on the freeware Unix in 1975. Even AT&T kept on developing Unix. You see the version 5 of Unix that became popular, and then the other vendors like SCO Unix, HP UX, Ultrix from Digital Corporation. Then you have AIX from IBM, and so on. Many variants of Unix appeared from 1975 version freeware that was made available. And as the PC appeared 1980s, the PC could not run Unix. It had a very simple operating system. Why can't Unix run on PCs? 1980s. What do you think? There were many reasons why Unix could not run on the PCs. One reason is that you need some support for virtual memory in the from the processor. It was not there in the processor before 8386. Before 386, the hardware support for virtual memory was not there. What is the hardware support you need for virtual memory? Can anybody answer this question? Basic, I mean first level question. Yeah, you need the memory management unit, and what are the functions of the memory management unit if it is asked? That is a separate question, as you were saying TLB etc. So, the paging support has to be there, and if you are not very sure about this is a very basic question. Please look up what is the hardware support you need for virtual memory. Typically goes by the name memory management unit, but what are the different units in that memory management unit? Please check that up. And also the PC had too little, I mean it ran on initially on floppy and then a hard disk, could not really run Unix, which was a large code. Unix was initially meant for servers or mainframe computers actually. And since Unix did not run on PCs, and by end of 1980s, that is 88 etc., the PC had become powerful, and then there were many who were thinking of having Unix run on the PC. Linus Torvalds, who was a student at University of Helsinki, he from the operating system book of Tannenbaum, where the Minix operating system source code is there, based on Unix actually, mini Unix. So, he just made use of that and developed the Unix for PCs, and where the MMU was already supported in 83-86 onwards, right, 84-86, and he could efficiently use MMU and then develop the basic skeleton on which a virtual memory operating system can be run on PC. And from 1991, he made it available as a freeware. But remember that the code is not really based on the freeware that was made public by AT&T Corporation. He had his entire new code written based on the Minix operating system. but the initial version that he made it public, there is no networking support, only in 8386 compatible processors, and supported the Minix file system. And from that point onwards, it had a very special type of development, where the development occurred by many collaborating programmers on the net. Slowly TCP/IP protocol was added by somebody, enhanced file systems were added, SCSI controllers for high performance disk access was added, and it became a freeware, and it has so far played a very important role in the operating system area. The Linux operating system started from a student project or a student's own initiative. But before we look at the open source, we will see that open source real time operating systems are very attractive. Many vendors are actually developing based on open source software, open source operating systems. But before we give our 100% commitment to an open source, let us see the pros and cons, because definitely these are attractive and it would be nice to use this, but this also come with a bit of a penalty. Now let us look at that, because we look at both the open source real time operating systems and also the commercial real time operating system. One thing is that you save on license fee, and when you talk of an embedded product costing few hundred rupees or few thousand rupees, license fee is important. Now even if you save 10 rupees or 50 rupees on license fee, your product becomes competitive, a highly competitive embedded market. The other advantage is that you have the code available to you, you can easily tailor it, take some part, delete some part, modify parts, you can make the operating system more efficient for a specific application, adapt to specific situation. So these are the advantages of an open source, and there are many success stories based on this open source. For example, the Apache web server is almost the de facto. Anywhere you go, ask what is the web server you are using, say we run Apache web server, which is a free server. More than 50% of the world's web server runs on Apache web server. Similarly, you have Perl for live contents on the web. The bind, which provides the DNS for the entire internet, is a freeware. But there are also penalties. One is that it costs more for development. Why should it cost more for development? Because you might have to know a new device you are trying to use, the device driver won't be available until somebody makes it open source, and you possibly have to develop the device drivers, and then the development might be more time consuming here in the open source. You need to understand, right? Finding open source programmers may be more difficult, who need to understand the internals of this, right? So the labor cost may be more and difficult to find skilled manpower in open source. There is another factor that we need to remember, is about the open source license model. It is not that you just take the open source and keep on using it, but you have to abide by a license model, which requires that if you make any modifications to the code, need to publish that. So any development to the, for example, a free operating system, if you change it, tailor it and so on, you need to again make it freeware. That is the understanding. And if you are a commercial manufacturer and somebody says that, see, you make your software freeware, definitely it will be a big turn off. Say that, see, then what is the what is the advantage of using this? Competitors will get my software. So, there is a pessimistic result here. I mean, I do not know the authenticity of the result, but says that there is a decline in operating system, open source operating system use. But again, there are some other reports saying that there is a big increase in the real time Linux as a real time operating system, and we know that Linux has become very popular because operating system is a significant part of the desktop cost. So, as far as desktop is concerned, we can see nowadays many desktops that run only on Linux, the cheap ones. Okay, so that is for the debatable, and these are the controversial reports. Let us not get into that, but at least let us be aware of the issues before we proceed further. Okay, so let us look at the real time situation, operating system situation here. So, this is again a statistics published in Embedded System Design magazine. Says that the commercial operating system, that the priced one, constitute nearly 50%, slightly more than 40% are commercial operating system, and then there are many of these applications which have none of the operating system. Internally developed operating system is about 15, and then open source is only about 10%. And among the commercial operating systems, if we look at the embedded systems, we will see that the Microsoft's CE operating system, Microsoft Embedded or the WinCE, that has the largest following, more than 25% here. And then the Wind River is a big player. As we proceed with our discussion, we will discuss about the Wind River operating system, the Symbian operating system, Green Hills, the Palm OS, etc. And then there are also many other players, as we are saying, which have uses in some specific situations. Now, as we were saying that we need to understand some very basic issues on Unix operating system, and then we need to understand why Unix as it is not a suitable real time operating, what is lacking there internally, and then based on that knowledge we can appreciate the real time operating system. So, this is a very basic concept. We know that any kernel, when we talk of what is a operating system kernel, a kernel is the memory resident portion of the operating system. The kernel is memory resident, and it is basically the manager of the resources, right, the hardware resources, the data resources, and so on. And the operating system, if we look at it, there are the kernel, there are three main components of this: the file system, the process control system, and the device driver system, and the memory management, of course. So, I think it would have been better if we wrote file system, process control system, and the memory management system. Okay, so this should be the file system and the memory management system. And then if we look at the process control system, we have the scheduler here. Okay, we have put the memory management under the processor control system, inter-process communication, and so the user program, they have some libraries or the system calls, right. These are the libraries supported by the operating system. And then, as we were saying, that once you invoke a operating system library, it traps into the kernel mode through a software interrupt. So, the mode changes from a user mode to a kernel mode through a system call interface. And then there are various data structures that are maintained. For example, there will be various memory tables that need to be maintained, which memory, which page is being used, how frequently, all those things, IO tables, IOs that are being used, who is using, etc. The file tables, which files are open, what is the current access block of the file, etc. The processes, for every process, process tables are maintained. For example, we have the process images that are maintained, the user data, user program, the system stack that is used, and the control block that is being used for this process control block. Now, how does a system access its resources? Through a system call, this we are discussing, right. A user process can access system resources through system calls. A user process cannot directly manipulate the resources. It can only make calls to the operating system, and there are many examples of system calls. For example, fork, wait, exec, etc. File system calls, open, read, write, lseek, etc. There are other calls like a pipe call, dup, then mount device, etc., unmount, link. And we will discuss this diagram with a much more elaboration, but this is a basic issue here. Just see here, if we look at the priorities levels in a Unix operating system, see that there are two modes, the user mode and the kernel mode. And the user level, there are various types of priorities, right. User level 1, user level 0 to user level n. N is the lowest priority, 0 is the highest priority. And there are tasks, processes queued at various levels, right. There will be context switch among these levels of tasks. Okay. And then in the kernel mode, there are also various priority levels. All kernel priorities are higher than the user priority. Just check here, there are two different bands. And then among the kernel also, there are various priorities. The kernel processes are possibly the lowest priority. And then we have file IO, buffer management, disk IO, swapper has the highest priority. We will later on understand why really this kind of priority arrangement is necessary among the operating system processes. And then there are various tasks that are queued at various priority levels. So, this is a basic picture, we will remember it, and then we will elaborate on this as we proceed with our discussion. The scheduling policy that is followed is a round robin scheduling with a fixed time quantum, and the priority is dynamically adjusted. That is what we are saying. The Unix by itself does not support any static priority. As the task keeps on running, its priority value keeps going up and down based on what the task is doing. So, what the scheduler does is that it computes a CPU uses factor, that is how much fraction of its time or slice it could use the CPU. If it ran through the entire slice, then its priority will decrease. If it could use only hardly much of the CPU slice, because possibly it had to block for IO or something, its priority will increase. If it used the full slice, time slice allocated to it, its priority will decrease. If it could not use its time slice because of possibly it had to wait for IO or some event, its priority will increase. We will see exactly how it computes this, because this is important for us. We will see how the Unix computes this, the dynamic priorities. We will see that it uses a weighted history. It is not that what it did in the last slot, last slice what it did, but what it did in the last to last, and before that the history is used for computing the uses factor. And then the super user processes are run at kernel priority, which are more than the user priority. The kernel is typically 0 to 49 and the user is 50 to 127. The entry to the kernel can either be synchronous or asynchronous. In a synchronous entry, the kernel performs work on behalf of the process. For example, make a system call, that is a synchronous one, or some hardware exceptions, let us say divide by 0 error exception need to be handled. So, these are the synchronous ones, and these occur in the context of a specific process. See, this hardware exception occurred on behalf of the process, right? The process was running and the exception occurred, and similarly the system call was made by the process. So, in the synchronous one, where the current task waits for the operating system to do something, is a synchronous entry into the kernel. We can also have asynchronous entry to the kernel, where the kernel performs task unrelated to the current process. For example, hardware interrupt, where the kernel takes up the responsibility of processing, is asynchronous entry into the kernel, where it can run programs that are unrelated to the current process. For example, IO completion interrupt, status change interrupt, clock interrupt, etc. And we said that the OS kernel mainly differs in 3 principal ways from a traditional application. A user program runs in 3 main ways. The first one is that it runs in the supervisor mode. The kernel programs, kernel processes, they run in the supervisor mode. That is, they run at higher priority, and also they can do some privileged operations which the user programs can do, and the paging is not applicable to the kernel. These are memory resident. The user programs undergo paging, and these get fully loaded during boot and are resident, and also they can do some privileged operations, run at higher priority and do some privileged operation, like they can access the memory, entire memory, execute some instructions, access IO ports, etc. They do not undergo paging, and they are fully loaded even before the system becomes ready to operate. The 3 principal differences we will keep in mind between a user level process and a kernel process. Now, as we will discuss the different types of kernels, we will see that there are 2 main variations. One is the traditional monolithic kernel. In the monolithic kernel, the principle or the concept here is the kernel is the OS. If you talk of the kernel OS, it is almost the kernel, minus of course the cell, etc. Is the entire OS is the kernel. The idea behind a monolithic kernel is that the kernel processes execute efficiently and securely once they are in the kernel mode. So, it would be advantageous to keep as many processes and tasks in the kernel mode as long as they are required to do some important tasks. It is advantageous to have them in the kernel mode. That is the principle that is used here. But the main problem with the monolithic kernel, why this is going out of scope or it is getting outdated, we will see the all later operating system kernels are based on microkernels. Yes, please.
OS has many other functionalities like process management, file management, all those things.
Yes.
What is the kernel part of OS? What it includes?
Okay, we said that actually. So far we have already said that. See, the kernel is the resource manager, right? It handles the processes including scheduling, communication, etc. It handles memory, which is an important resource. It handles the devices, files, right. These are important responsibilities of any kernel. And then we have other things, for example, a cell, the user interface, right. We might have a compiler. Would you call it part of the OS? But it can also come with the OS, right. So, the kernel does not include the compiler, you said that, but it also comes with the OS. So, that is actually in the cell and cell utilities, right. Cell is the application, it is not really kernel, you are right. So, the kernel is the resource manager, which is resident. A compiler need not be resident in the memory.
So, OS is kernel plus applications?
Of course. It has the kernel plus some cell and cell utilities. The cell, the outer part of the OS, is not really the kernel. Okay.
Windows is monolithic.
Windows, Unix, etc., all these are monolithic. We'll discuss about this in more detail.
The entire part of the operating system is resident in the
Yes, yes. We'll discuss about this. So, the disadvantage, we are saying that, see, monolithic is becoming outdated. That concept developed long back, and the principle was that as long as these become part of the OS, they can do some privileged operations. They execute more efficiently and securely, because the user mode processes can't really affect them. The user mode processes run at a lesser priority, and also they are not privileged like these, but that thing is becoming outdated. We have most of the modern operating systems, including the real time operating systems, microkernel operating systems. The kernel is kept to the minimum, that is why it is microkernel. Now, let us find out what is the problem with this monolithic kernel. One is that it is massive, does many things, all the resource management activity, non-modular. See, all of them, they have access to each other's data, right, because all of them are privileged, they can access anything they want, and hard to tailor, because once it is in the kernel mode, right, you can't really add new things or take out some of these things without really recompiling your kernel. Kernel recompilation will be necessary, even if you want to make a small change to the kernel, even if you want to add a new device driver, need to recompile your kernel. These are difficult to maintain and extend. Of course, this goes with this, because hard to change it and extend. Yes, you can't really add without recompiling the kernel. And also, since these execute in the kernel mode, debugging the kernel is very difficult. Those who have worked with the kernel, they might know that, because how do you find out who has changed which part of the code, because all of this is a non-modular code, remember. The traditional operating systems are monolithic. One large kernel handles everything. We are saying that Unix and DOS. See, now we will see that slowly the Windows and Unix, they are becoming microkernel based. And the typical construct of these traditional operating systems, we even read in the first level course that they are a layered one. Functionality is decomposed into n layers, and each layer provides service to the layer above it and utilizes the service of the layer below it. That was the typical structure of an operating system we studied in the first level course. But we will see that the microkernel approach is become popular now. It is the minimalist kernel approach, as the name says, it is a microkernel. The idea is that run as much part of the kernel, traditional kernel, in the application space as a user program. The kernel is modular and small. from 10 kilobytes to few hundreds of kilobytes is the kernel. It is easier to port, maintain and extend because all others are user programs. You can just keep them, adding them and taking them out, the other part of the operating system, without really having to compile the kernel. Stop your operating system and compile the kernel is not necessary. But we will see that in the microkernel approach, you will find huge literature on this, but you will see that there is no really general agreement on what should be in the kernel. But typically you will see that the process management, memory management and some inter-process communication is part of the kernel. But we have also situations where a microkernel where only the basic process handling facilities are there, rest everything is in the user space. We will see that. So, if you look at the monolithic kernel approach, you see that the operating system is in the, all of these are in the kernel mode, starting from device driver to network driver to graphics driver, terminal driver, memory manager, process manager, file manager. Everything is in the kernel mode, which directly interact with the hardware layer, hardware interface layer. We called it as the BSP or something last time, board support package, and these interact with the hardware. And then the applications run on the user mode or user space, but they can make system calls to access the operating system services. In the microkernel approach, we have a tiny kernel here, possibly does some very basic process management, but see here process management, and we are saying that the typically accepted functionalities are basic process management and some memory management, that is what we are saying. But see here all these are running in the user space. The network drivers, graphics drivers, device drivers, file systems, the file system manager, memory manager, network manager, device manager, all these are running on the user space, and then the applications are invoking them services directly without a system call. We will elaborate on this model later on. So, this is another view of that.
Then what is there in the kernel part? All the
Okay.
file management, memory management,
See, as we were saying that some very basic process handling, process creation, process scheduling, etc., and also very basic memory functionality are here. So, that is the accepted view of what is a microkernel, the rudimentary process management and some part of the memory management.
It supports the memory manager in using.
Yes, exactly, yeah. This is another view of the microkernel, where we have the microkernel and there are various types of memory protected applications here. We know that all these are in the user space also, they are memory protected, and they just keep on communicating with each other through a message passing bus. This is a high level view of the same thing. Now, with that basic idea, basic concept on operating systems, microkernel and monolithic kernel and the basic services and so on, let us see why Unix is not suitable for a real time operating system from the internal point of view. Not like that it you can't really run real time schedulers, static priority level not available, etc., or some other facilities not available. We will see internally what is holding Unix from being used as a real time operating system. So, if we analyze the reasons, we will see that there are two main stumbling blocks. Other things to quite satisfactorily, or to some extent they can be taken care of. Other facilities, I mean other features of Unix can be extended, but there are two main stumbling blocks. One is a non-preemptable kernel and the other is dynamic priority levels. So, let us check why the Unix is non-preemptable in the first place, and what is the difficulty to make it a preemptable, and then why this dynamic priority levels, can't we just have static priority levels in the Unix, and what does it do with these dynamic priority levels, why does it need in the first place, how does it help. So, let us understand those issues, because if we understand this, we can very well understand the real time operating systems and how they have developed and what is there inside them, how they are different from the Unix. Let us look at the non-preemptable kernel part. We had said that even a user program can execute in a kernel mode by making system calls, and the original Unix developers did not visualize the use of Unix in real time and multiprocessor systems. So, what they said is that when it is running in the kernel, then it is the operating system or the one that is most privileged one is running, it need not be interrupted. The user programs can be interrupted, but the kernel let it complete and then it can examine the interrupts, etc. So, the simplest thing they could do was to disable the interrupts once in the kernel mode. The idea was that if they allowed interrupts even when it is in the kernel mode, then they will have to do extensive locking of the kernel data structures. Otherwise, the kernel data structures will lose their integrity. Like let us say one interrupt has occurred, another interrupt is handled, or let us say one process has not yet been created and you want to create another process, and so on. The data structure will become inconsistent, and locking would make it inefficient. So, why go for this inefficiency? It is not required, because after all the kernel is the privileged one, it should not be interrupted. But when we talk of a real time application, it would lead to deadline misses, because the task preemption time will become the time spent in the kernel mode, that is once you made the system call, it will execute in the kernel mode, and then the context switch time. Once it completes the kernel mode, then only the context switch can occur, and the time spent in the kernel mode can be of the order of a second. For example, it has initiated a read call or a write call, can take a second or maybe several seconds. So, that much time the task cannot be preempted, and by that time a real time task miss its deadline. Now, let us look at the dynamic priorities. I think we are adjusting our time today. So, since this is a important issue, the dynamic priority handling in Unix, which we need at least 15 minutes discussion. It is an important topic here. Why dynamic priorities are needed, it is the advantage, and do we need this in the real time situation? We will see that we will also need in real time, some real time operating system dynamic priority levels, and we will understand what is the advantage of this and disadvantage of this and how it is supported, how exactly the dynamic priority values are computed, because the same formula is used across all operating systems, traditional operating systems. So, come to a logical point, we will stop here, we will start our discussion from this point onwards in the next class. Okay, thank you.